Okay, so let's look at the fundamental theorem of calculus. Uh, this is section 5.3, part 1. And we're going to look at the part 2 of the fundamental theorem of calculus. We'll take care of looking at part 1 another time. And it says this: if you have a function f that is continuous on the closed interval a to b, then the integral from a to b of f of x dx is equal to f of b minus f of a. And we've learned that that capital F is the antiderivative of the function f, the small letter f. So let's see how this works. We have the integral from -2 to 1 of x cubed, and I know that x cubed is continuous everywhere because it's a polynomial function. So we go ahead and we take the antiderivative of x cubed, which would be 1 over 4x to the fourth, and we're going to take that from -2 to 1, and we draw this straight line like that. What we'll then do is we'll take that 1 and plug it into x to the fourth, or plug it in for x, excuse me, and we're going to subtract whatever we get when we take and plug in -2 for x. So when I evaluate the left portion, I end up getting 1/4, minus evaluating the right portion, I get 16 over 4. So my final answer is -15 over 4. And again, as we know, this gives us the area under the curve of x cubed from -2 to 1. So that must mean that the majority of the area is negative. The next one over there, we have from 2 to 4 of x squared dx. So the antiderivative of x squared is 1 over 3x to the third. We're going from 2 to 4. We'll take and we'll plug in 4. So I have 1/3, 4 to the third, and then we are going to subtract what we get when we plug in 2. So what I end up with is 64/3 minus 8/3, which would be 56/3. So the area under the curve of x squared from 2 to 4 is a positive 56/3. Next one we have from 1 to 4 of x squared plus 2x minus 3. The antiderivative of that function is 1/3 x to the third plus 1x squared, because the 2's would end up canceling out, minus 3x. And I'm going from 1 to 4. Take and plug in 4, so I have 1/3 multiplied by 4 to the third plus 4 squared minus 3 times 4. And we are going to subtract what I get when I plug in 1. So this is going to go off my screen here, but 1/3, 1 to the third, plus 1 squared minus 3 times 1. Sorry about that. When I simplify the left-hand set of parentheses, I get 76 over 3. And when I simplify the right-hand set of parentheses, I end up with minus -5/3. So plus 5/3, which ends up being 81/3, which is 27. So no longer are we using sigma, we're going ahead and using the concept of antiderivative to calculate these things. Find the area under the parabola. Y equals x squared from 0 to 1. So what we need to first do is set up that integral. So that means I'm going from 0 to 1 of x squared dx. And then we go ahead and use the concept with that antiderivative that we just had. So the antiderivative of x squared is 1/3 x to the third. I'm going from 0 to 1. Plug in 1, and I get 1/3 1 to the third minus 1/3 0 to the third, which final answer then is 1/3. Example 3. Area under the cosine curve from 0 to b, when b is between 0 and pi over 2. And that's important because 0 and pi over 2 is in here, in this first quadrant here, which means that whether it's sine, cosine, or tangent, the answer would be positive. So, cosine curve from 0 to b, so cosine x dx. And we know that the antiderivative of cosine is sine, so we're taking sine of x from b to 0, or 0 to b. Plug in b, so I get sine of b. Plug in 0, I get sine of 0. And if I look, the sine of 0, that's right here, that's the 0.10. Sine is the y value. So this second portion here is equal to 0, and I'm left with just the sine of b minus 0, or the sine of b. Area between the x-axis and y equals x squared minus 10, well, that's what we've been doing all along. So and I'm going from 1 to 3, so x squared minus 10 dx. We just need to make sure we know how to set it up. Go ahead and take the antiderivative, 1/3 x cubed minus 10x, and we're going from 1 to 3. So go ahead and plug in 3. So I have 1/3 multiplied by 3 to the third minus 10 times 3. And then plug in 1 minus 1/3 1 to the third minus 10 times 1. Simplifying both of those, you end up with negative 21 plus 29/3. Well, this is negative 63 over 3 plus 29 over 3. So my final answer is negative 34 over 3. Same question between the x-axis and x squared minus 9. So we just set up the integral x squared minus 9. We're going from 1 to 6. Antiderivative is 1/3 x to the third minus 9x, going from 1 to 6. And again, just go ahead and plug in 6. So 1/3 6 to the third minus 9 times 6. Plug in 1. And when we simplify that, we have 18 plus 26 over 3, because this was minus a negative 26 over 3, giving me a final answer of 26 2/3. The next one, find the area between the x-axis and y equals the square root of 4 minus x squared. I think I should do something like this, but they don't give me what I'm going from, the limits that I'm going from a to b. So what I'm going to go ahead and do instead is go ahead and look at what does this graph look like. 4 minus x squared, the square root of that actually is a semicircle. That looks like this. So really what they want to know is what is this area? And we learned about this before, that we can just go ahead and calculate that using the formulas we know from geometry. That's a semicircle. So that area would be pi times the radius squared, which in this case is 2. And since it's a semicircle, I would divide by 2. I end up with 2 pi, which is approximately 6.28. The last example here, what's wrong with the following calculation? Well, it looks like they went ahead and did the antiderivative correctly, but what we haven't been paying close enough attention to probably is that this here is discontinuous when x is 0, and since the limits include 0, this does not exist. We can't calculate this. So discontinuous at x equals 0, so does not exist. And if you look at what this graph looks like, the graph of 1 over x squared actually looks something like this. So we have it looking like this and this, and if we're going from -1 to 3 and we tried to calculate the area between the curve and the x-axis, we would find that this open space up here, it would go up to infinity, so we can't calculate that.